So, in our previous session, we have already implemented various libraries which are used for data science and machine learning. And in our this segment, we are going to understand what's the maths behind data science and machine learning. So, we have already discussed this data science thing. Okay, data science, na? That means exploration of the data. Okay, and machine learning is something that we are expecting the machine to gain some knowledge and perform the task according to whatever the knowledge the machine has gained. Okay, so first of all, if I do talk about the data science, as I told, exploration of the data. So how to explore the data, what are the features present in the data, what are its characteristics, and after knowing all the terms, then we need to apply some maths over it. Because the reason is, unless and until you don't do or perform calculations over the data, how you are going to get the results? So obviously maths is required. And in case of machine learning also, the machine requires the data feeding. Okay, and then it will process the data according to the algorithms. All right, so what these algorithms are made up of? Okay, the programming, the coding which you are doing based upon the algorithms are made up of whom? They are also requiring in a requirement of the maths behind it. So mathematical equations, they have been derived from these equations, and different set of variables are used, and different uh, your functions methodologies has been used. On the behalf of that, we are applying the techniques, we are deriving the algorithm, okay, and then converting it into your programming concepts, and then obviously we are going to apply the data over it. Now, anyone is having doubt, please let me know. If someone wants to ask anything. Okay, so here, because the base or the foundation of data science and machine learning is totally based upon your mathematics. Okay, so that makes the maths importance. So the point is, machine learning theory, if I do talk about it, is a field that intersects the statistics also, probability also, your computer science algorithms, programming, everything. Okay, so this machine learning is a combination of all everything. All right. So ultimately, what was our goal in machine learning? That means we are going to build an intelligent application, intelligent machines, okay, those who are going to respond to us when we are going to feed the information. They should give me the results, some intelligent results. That's what I'm going to. Intelligence means, that's not about, I'm talking about the human intelligence. That is something related to the machine intelligence. That's what I'm expecting from the machine. Because machine is naive. Okay, it doesn't have any brain, something like that, but we are making machine intelligent on the basis of the data feeding, okay, and learning based model. Okay, so the point is, as I told, that maths is required, some computation calculation is required for that. Okay, so the thing is, what is, or why we are worried about the maths too much, and what is the level of maths being required in the data science and the machine learning? So, and how it's going to help us, okay, in deriving the algorithms and performing the predictions and whatever been we are required from the machine. See, the point is, there are many reasons why the mathematics for machine learning is important, both for data science and machine learning. There are many reasons. The first reason is, if you are going to select the right algorithm, which includes given considerations to accuracy, training time, model complexity, number of parameters, and the number of features. See, the point is, uh, we need to apply modeling over, that means we are available with the data and we need to apply a model. Okay, So, which algorithm is better suited for this problem statement, whatever be the problem statement given to us? Okay, in the terms of accuracy, training time, complexity, okay, and the number of parameters which are needed to be applied on that particular model. Okay, so obviously, a model is an algorithm which has been prepared on the basis of mathematical equations. Okay, and this algorithm has been converted into programming concepts. Okay, into some programming language. And then we have converted that program, that file, into a library. So, what you were doing previously, you performed import numpy as np, you performed import pandas as pd. So you have performed this importing of the files or the libraries. Okay, so you know, obviously these files or libraries or packages are built on the basis of on some algorithms, and algorithms are derived. What is an algorithm? It's a step by step solution of a particular problem, and algorithms are derived from some equations, some math is behind that, which are solving some problem. Okay, so here selecting a right algorithm for your problem statement is important. Which algorithm, which model is going to give me the best result is something which is we are in an expectation. Okay, in case of machine learning, we are having supervised machine learning, we are having unsupervised machine learning. In supervised also we are having various algorithms. We face a problem of classification and prediction in case of supervised machine learning. Okay, in case of unsupervised we face the problem of clustering, okay, segmentation. All right, so obviously they have some specific algorithms which are listed. Okay, but which algorithm better suits from my problem statement? This makes a sense. Okay, so different algorithms have different, mathematical according to their concept. So selection is very much important. Second thing is choosing parameter setting and the validation strategies. Okay, what parameters are required to give in those algorithms, in those mathematical models. Okay, so choosing parameter setting, every algorithm has different set of parameters, okay, on which they are been derived for, on which they are working. For example, if I do take a model, linear model, okay, so it has a different set of parameters. If I do take non-linear model, for example, decision trees, random forest, so they are having different set of parameters. Okay, so those algorithms are built on different set of parameters, and these parameters I need to be input in the mathematical equations. Okay, you know that if I do talk about a linear equation, y equal to mx plus c, this is a general linear equation. And what is x and what is y? Sir, x is independent variable, and sir, y is dependent variable, which is dependent on x. So, x is a parameter, no? X and y. Though both are the parameter, if I do change the value of x, obviously it's going to reflect on the value of y. And m and c is a constant, m is a slope. Okay, so this is one of an equation which I told if I'm working on a linear regression problem statement. So obviously this linear equation has been used there. Okay, so linear regression has been built on the basis of linear equation. All right, so it has having certain parameters. So selection of parameters, choosing a parameter, what value has been required there, it's very much important. And the number of features, because in a data you might be having multiple features. Okay, 5, 10, 15, 20. What features are important for me to perform my modeling purpose is something really important. Okay, so number of parameter requirement and number of features requirement, these are important, and you need to set them accordingly. All right, so first is your selection of the algorithm. Second, after selecting algorithm, what parameters you need to give to that algorithm, that's important. Your third one is identify the underfitting and overfitting. Now, underfitting and overfitting, just listen carefully. Underfitting, that means if you are having a scarcity of the data, you are not available with the amount of data for which that model is been required to get well trained. Okay, that means you are lagging, or that means the point is data is unavailable for you to make your machine understand, okay, different problems. So that is called as underfitting. Okay, and overfitting, that means the point is, and your model performance is also not best in that particular case. In case of underfitting, that's a worst scenario. Okay, your accuracy of the model is least. And in case of overfitting, that means your model is performing nearly an accuracy about 100%. That is called as overfitting. So this is the difference between underfitting and the overfitting. When your model accuracy is likely to be 100% accurate, okay, so that's overfitting. And when your model accuracy is less, very less, so that is called as underfitting. So the point is underfitting and overfitting. Yes, someone raise the hand. Please let me know. Yes, ask the question. So in case of underfitting and overfitting, uh, your model makes accurate but initially incorrect predictions. Okay, incorrect predictions in case of underfitting. And in case of overfitting, your model does not make accurate predictions. In case it consider some those data points also, uh, which I believe that can be raised because of an error. Okay, so overfitting, you should be understanding that your model giving the prediction nearly about reaching the accuracy 100% accurate. Okay, and and the point is your model is not making accurate predictions, while in case of underfitting, the model is making accurate predictions, but initially incorrect. Those are incorrect in nature. Or I would say, if I just change the terminology, underfitting is a scenario where model is unable to capture the relationship between the input and the output variables. As I told, that if you're not available with the amount of the data, so understanding the pattern in the data, okay, how this your um, dependent and independent or input or the output variables are related to each other. Okay, so that's the case. Okay, so just let me reshare the screen. Okay, so that's the issue related to your overfitting and the underfitting. That means ultimately we are not getting the desired results. All right. So, so the point is why this thing happens, because of the base and the variance trade-off. Okay, so what is this base and the variance trade-off? See, understand it. It's a actually fundamental concept in machine learning that relates the performance of the model. So we are talking about the overfitting and underfitting. That means we are talking about the performance of the model. Okay, and actually we are looking forward for the results, whether the predictions done by the model are correct or incorrect. Okay, so if your model is giving you faulty results, okay, That means wrong predictions. On the basis of that only, we are saying that your model is either underfitted, whether your model is overfitted. Okay, so underfitting is the case when your model accuracy is very much high, and we never believes that any of your machine is going to give you the 100% result. No, if you are having an accuracy more than 90%, 95%, something like that, we are saying that your model is reaching towards the state of overfitting. Now, um, base and the variance, this trade-off, see what does this base means. See, base refers to an error which has been introduced by approximating a real world problem with a simplified model. Okay, so base is actually an error. Okay, so model with a high base tends to oversimplify the problem. Okay, that means a model which is giving high base, that means high errors, high range of errors. This is the case, leads to the underfitting and poor performance of both training and the testing data. Okay, so that means we are having errors are more in case of underfitting. All right, so models with a high base tends to oversimplify the problem. All right, so the results which we are getting here, in case of underfitting, because of the base, that means base is an error thing. Okay, so our results are incorrect results. While variance, on the other hand, refers to the error that is introduced by the model sensitivity to small fluctuations in the training data. That means variance means distribution of the data ultimately. Okay, so the model with high variance means high distribution of the data gives overfitting of the data, leading to the excellent performance, as I already told. In case of here underfitting, my model performance is poor. That means here the accuracy is less. All right, because the reason is your model is not able to judge the relationship between the data points. Okay, so here the performance is poor. While in case of the variance, the distribution of data is high. Your model is assuming that yes, I am confident, I can understand the relationship or the patterns in the data, and this is the accuracy, highest accuracy I am giving you. All right, but actually that's something we believe it's wrong. So wrong predictions are also been considered that kind of model if it has been trained over such kind of data. All right, so that's a variance thing. So this is called as base and a variance trade off. So either your data is been less, or if your data is more, so this is how your model is going to perform. So the goal is to have a right balance between the base and the variance. So error should be you know no, we are not going to have errors, more errors. So our target is to reduce the error. Okay, so base reduction should be there, and accordingly we need to adjust the variance. Okay, that should result in the best possible predictive performance of the data. So if you are getting an accuracy near about 90 or 80 or 85, something like that, we can see okay, fine, this is and an accuracy which is good performance of the model. Okay, neither very less, 60, 70, so that's less accuracies. That means your model is underfitted. And if you are having accuracy more than 95, 98, 99, or 100%, that means your model is overfitted. So you should be understanding these terms, because when we are going to perform the projects, you should be understanding that what I said for the overfitting and what I said for the underfitting. So just remember what is base and the variance thing. One is the error and one is the distribution of the data, and we need to keep a balance between both of them. All right, your next point is estimating the right confidence interval and uncertainty. Okay, and why we are understanding these points. These points are based upon your maths. Okay, statistics, and they are used in model development. Okay, so that's why I told that maths and stats are the foundation of machine learning and the data science. Your next point is estimating the right confidence interval and uncertainty. Now what does this mean? See, confidence in statistics, if I do talk about confidence, it refers to the degree of uncertainty that a population parameter falls within a certain range of values based upon a sample data. Okay, so you are available with the sample data, and you are checking for a particular value. That means degree of certainty that a population parameter falls within a certain range of a sample data. Okay, so the point is, considering a value and expecting that this value is going to lie between this particular range, that will be the confidence. So the level of confidence is totally expressed as a percentage, okay, that represents that represents your probability for the true population parameter falls within the confidence interval or not. Okay, so I will give you an example here. A 95% confidence interval means 95% probability that the true population parameter lies in an calculated range of values. Okay, and for the demonstration purpose, I'm having an example for you. Let us suppose there is a researcher and who wants to estimate the mean weight of all adult in a certain city. Okay, so you are in a city, and I want to find the mean weight of all the adult men which are present in the city. Okay, so the researcher collect the data of 100 adult men. Okay, 100 people, 100 men. I collected the data and calculated the weight of all the 100 men. That was coming to be like 175 pounds, for example, with a standard deviation of 10 pounds. Okay, so what my research was, my research was to estimate the mean weight of all adult men in a city. However, I started with picking 100 men, 100 people. Okay, and I calculated the weight of them. I calculated what is the average, and I calculated the standard deviation for them. All right, now what will happen next after performing this calculation? Now, to estimate the population mean weight with 95% confidence, okay, there is a rule in case of confidence, that is 95%. Okay, so 95% confidence interval means that 95% probability that the true population parameter lies. That means there is a 95% chances that your value, whatever the prediction which you are going to perform, that will going to lie in that particular range. Okay, so how to do this task? Okay, so here the researcher wants to estimate the population mean weight. Okay, so how population mean weight? Initially I took only 100 people sample. My task is to check out for the population mean weight. That means for all the men which are present in the city with a 95% confidence. Okay, for that reason, based on a sample size minus one, that is, there is a t distribution with 99 degrees of freedom. There is one more term available in case this of the statistics, that is a t distribution with 99% of the freedom. Here, what I need to do is, for a 95% confidence interval, the value came for its calculation is 1.984. Okay, and the standard error of the sample mean is calculated as a sample of 100 people divided by the square root of the sample size, which gives you 1 pound. Okay, square root of the sample size. Okay, which is sample size, the size of the sample. For example, you took 100 people, so square root of the sample size, for example, 100 square root is 10. Okay, and accordingly they have calculated that the weight of the person is approximately, they took it's like 1 pound. Okay, so the confidence interval was calculated like something like this: 175 plus 1.984 into 1. This is the interval between which the population mean weight is going to lie. This is 95% confidence. All right, so the point is, here I am looking forward for population mean. Okay, and I took the data of 100 people. I calculated the average weight of the 100 people. I calculated the standard deviation of that 100 people. And accordingly, now I am going to perform the estimation of population mean weight of population mean. Population. That means now I'm going to consider complete population. And I am expecting that the mean of the complete population with 95% confidence, I'm 95% confident that it's going to lie between this particular range. Okay, see, whatever happens, that there are okay, surveys for any kind of topics. So it doesn't mean that survey has been calculated for a complete city. For example, in your city, every city comprises of many people, and if someone do a survey, they do survey for some thousands of people. Okay, 1,000, 2,000, 4,000, 5,000 people. Now you will say whether my survey is completed. Just by picking 4,000 people, there are 4 lakh people in my city, and I did survey with 4,000 people. Doesn't mean that my survey is completed and it will give me accurate result. Okay, behind that there is a statistics applied, and that statistics is this thing, confidence approach. Okay, so they did perform survey on 4,000 people. Okay, and then they told that what is the level of confidence that if I do consider the population, and if this survey has been conducted over the population, what should be the results going to lie between what range to what range of values. That is what this survey or the confidence is going to give. So it's a complete maths. Okay, and this relates with the distribution of the data, and distribution of data is something very much important in the statistics. So definitely maths and statistics are something which has been important. So we are doing everything over the data, we are considering everything on the behalf of data only. Machine learning, data science, they are totally dependent on the data. So, and someone who understand the data is only the person is called as a scientist. If you don't understand the data, na, you are neither scientist, neither you are a machine learning engineer, you are nowhere. Okay, and just only understanding data completes everything. Remaining is your skill set, your coding skills, everything. But understanding data is very much important, and for understanding data, obviously you should have a knowledge of maths and the statistics behind it. So that's why we are going to study. I picked this 4 points because the reason is why you are here, to understand the maths behind data science and machine learning. So these are certainly some of the points which are important for us to understand the maths for your machine learning and the data science. Now, what is the level of mathematics you require for that purpose? See, in case of machine learning, as it's an interdisciplinary thing. Okay, so the amount of maths which is necessary for you, and the level of maths needed to understand for you, is something like this pie chart. Okay, so here you should have some knowledge of linear algebra, probability theory and the statistics, some multivariate calculus things, some algorithms and complexity, and remaining mathematical concepts which will be covered in others. Okay, so here it is stated, okay, to the learning level, that is a minimum of maths needed for the machine learning should cover all these topics. Okay, minimum all these topics should have to be covered. All right, so about 15, 15, and 25% near about. Probability theory, statistics 25%, it's max. Remaining all are 15 and 10% ratio. Linear algebra is 35%, you should be knowing. So we will be starting from linear algebra itself because it contributes to 35% of your machine learning and the data science stuff. All right, so it is something very much important. So 35% here and 25% for the statistics, probability theory and the statistics. So both of them will be going to contribute about 60%, and remaining all is your calculus and algorithms, and all these are near about 40%. All right, so considering the importance of linear algebra, this will be our first topic, and in this maths series we are going to learn about all these things, that is linear algebra. Okay, which we are going to include the vectors, matrices, eigenvalues, eigenvectors, everything. Okay, in calculus, I hope you know about all these terms, that is differential calculus, okay, integral calculus, you have a knowledge of that. Probability and the statistics, obviously, that is the foundation of statistical inference. Okay, probability thing, that means based upon the outcomes. Okay, so now obviously many of the algorithms have been prepared in machine learning and the data size based upon probability only. Okay, so we need to learn the probability also. Then multivariate calculus, that means I'm going to extend the calculus to the functions to more than one variable, because here we will be dealing with the optimization problems in case of machine learning. And what will be our goal? The goal is to find the optimal values for multiple variables. So we need to know the multivariate calculus thing also. Calculus, to be very basic, you know about how to do integration, how to do differentiation, and remaining all rest of the all we are going to cover in this topic. Optimization techniques, that means to find the minimum or the maximum value in the function, very much important, very much important. Okay, so it is used in the machine learning to find the best model parameters and to minimize the cost function. Now, what is this cost function? Obviously, as I told, that you are having base and the variance trade-off. Base means an error, okay, and my goal is to reduce the error. All right. So the thing is, and cost function is the average of all the loss. Loss is the your difference, or that's an error thing. Okay, so cost function is an average of all the losses, all the errors. So my task is to minimize the loss. Task is to minimize the loss cost function. So for that reason, I need to perform the optimization. Okay, so it's also very much important. Information theory, just to quantify the amount of information. Okay, that's also be needed here. Graph theory, obviously, it is used to develop the algorithms such as clustering, classification, anomaly detection. See, in machine learning, we are having different kind of problem statements. Either it's related to classification, prediction, clustering, anomaly detection, depending upon your supervised and unsupervised algorithms. All right, so this is graph theory thing, and now some numerical methods. All right, so those problems which we required to solve, on the basis of numerical techniques. Okay, numerical approaches. So they are also going to relate with optimization algorithms and solving the differential equations. Okay, so some things which we cannot solve analytically, that requires numerical approaches. Okay, so I hope most of the points which has been mentioned here you have already studied in your maths, in your engineering, but still we are going to explore all of them in this series for the maths, for data science and machine learning. And we are going to get started with the your linear algebra part. Okay, so what is this linear algebra? Very much important. As you have already seen, 35% of the contribution of the maths is done for the linear algebra. So here we are going to do your study for linear systems of equations. All right, that means it's a branch of mathematics which deals with a linear system of equations. Okay, and what we are having in this topic: vectors, lines, planes, all these things which are going to represent your real world phenomena and which are going to optimize your machine learning problems, algorithms, we are going to use in the linear algebra. Okay, because the point is our data, the data which is given to us for training the model. Okay, that might be huge, large data set, and we need to structure it in such a way for the simplification means. Okay, so either we can organize the data into matrices, vectors, and there are many, we need to perform various transformations over the data. And data is not mandatory in any numerical format. Data can be in a text format, data can be in image format, data can be in a video, audio, whatever. Data is data, it can be in any format. So obviously we require some algebraic equations to transform the data into some meaningful output. All right, so in order to transform them in a meaningful output, obviously I need the linear algebraic part. All right, so that's what our goal is. So linear algebra is a building block. Okay, it comprises of vectors, mathematical objects that describe both direction and the magnitude, you know that. Okay, what kind of quantities we are available in the mathematics? We are available with the scalar quantities, we are available with the vector quantities. Scalar quantities are those quantities which only have a magnitude. Okay, we can have a numeric representation of them. For example, if I say 2, so 2 is a scalar quantity. If I say 2 I cap, so now you will say, sir, 2 I cap ma, so it is having magnitude and direction both. Okay, so vector quantities are those quantities which are having magnitude and direction. That means if I going to represent this magnitude 2, I need to represent it in some direction. Okay, that means it is having directional space. All right, so it's a vector quantity. All right, so it has very applications. These vectors, that means quantum computing requires vector spaces, and here in machine learning and its associates obviously requires this vector notations. All right, here it is. You can check it out. This is a 2D vector space. If I do talk about a 2D vector space, and here is 1 2, 1 2 is a vector, 1 2 is a vector. So if I'm going to represent this 1 2 in a vector space, this is how you can represent it. Okay, here 1 2 is represented in a vector space. Similarly, minus 3 and minus 2. Okay, so you understand about the coordinate system. This is a 2D coordinate system. Okay, in 2D you are available with the x-axis, you are available with the y-axis. Okay, so if I say that one is in on x and 2 is on y, so this is how you can represent 1 2 in a plane, in a 2D plane. Okay, and if I create an arrow, if I join from the origin, okay, if I join from the origin, then it will be a vector. This is a vector notation where that point 1 2 is associated in a plane, where it's actually located in a plane. Similarly, I can draw an arrow from the origin to mark minus 3 and minus 2. So this is actually a vector thing. All right, and we can apply most of our mathematical operations on vectors and the matrices. Okay, so these are the animations by the help of which I'm making you understand that how to perform the task over the vectors. So for example, if I need to perform the vector addition, okay, so this is my 1 2, this is my minus 3 and minus 2. So I can perform addition over the vectors. I hope you know this thing: vector addition, vector subtraction, vector multiplication. Okay, you know these terms. All right. So if I need to perform the addition of these, so 1 2 and minus 3 minus 2, it's going to give me a result like it's been mentioned, minus 2 and 0. All right. And how to represent it into this plane, minus 2 and 0? This is the line. Okay, this is the line which is in your red color. You can see very light red color. This is your minus 2 0. This line is minus 2 0. Okay, so one direction from the origin of 1 2 is here. One direction of the minus through minus 3 2 is here with the yellow line, and the red line, light red line. This is your result, minus 2 0. This is how it's represented in the 2D plane. Okay, addition of the two vectors. Okay, so with the your graphical this representation with the GIF representation, this is how we are understanding that how to add your vectors and how to represent them in a plane. All right, so here each vector has an arrow pointing to a certain direction. Obviously, as I already told, that a vector is having a direction. Scalar with a direction is a vector quantity. Now, direction of a vector after addition. This is very much important to understand. All right. So here, if you want to check out, this is a plus b. Okay, you can see that if I'm having this is a, this is b, so resultant is a plus b. This will be the direction of your vector. Okay, and we have already studied these terms in physics also, and we have studied this thing in your maths also. All right, so you can see a followed by, then b is followed. Okay, and then this is a plus b direction. If I would say this is a, this is b, so this direction will be b minus a. See, you need to understand and you need to remember, that direction is everything. Understanding the direction is everything. Okay, so if a is on this direction, b is on this direction, so this direction will going to represent you b minus a. And if I reverse the direction, then obviously my terms will be reversed. This will be a minus b. Okay, this will be a minus b. All right, so if I'm writing, like, if I need to add the two vectors, the direction should be like this. If I need to subtract the two vectors, direction will be like this. This is b minus a and this is a minus b. Just focus on the direction of the arrow, of the green arrow, what it's telling. All right, so this is vector addition and the subtraction. Now the thing is the property of vector operations. Okay, so there are various properties which are available in the vectors, and these properties are commutative, associative, zero element, distributive, additive, identity, okay, and additive inverse. Okay, so commutative, that means a plus b equal to b plus a. This is commutative, or rather I would say a into b equal to b into a. This is commutative. Associative, that means a plus, then there is a bracket b plus c, that is equal to a plus b plus c. That means there is a bracket between a and b. Okay, so you can have a vector a, b, c. These are the vectors, and if you write them in this notation, now it will follow the properties. So vector operations follow these properties. Okay, same thing with the multiplication and addition both. Zero element, that means an identity element. A plus zero equal to zero. So if you add a vector with the zero, it's going to be give you the same vector. And if you multiply a vector with one, now it will give you the same vector. All right. Distributive property a dot b plus c, that will be equal to a dot b plus a plus c. This is distributive in nature. All right. And identity a into 1 into a is equal to a. This is identity. All right. And the last one is additive inverse. That means if you add the same vector that is having a minus sign, the result will be 0. A plus minus a equal to 0. So these are the vector operations, vector properties. All right. So, many students are unsure of what constitutes a linear equation. So, I hope you understood that is what is this linear algebra. Okay. And that means algebra, equations. Okay. Some notations related to the equations. We are having some expressions. Okay. We need to solve them. That's related to the algebra. You are having some line. You need to represent those stuff on the graph. Okay. So, this relates with the algebraic thing. Okay, we have studied the scalar, we have studied the vectors. Okay, and there is some issue with the students in misunderstanding what that issue is. See, many students are unaware of linear function. What does this linear function means? Okay, so common misconception is that it must be a result of straight line. So linear function means a straight line, because there is a linear term now. So straight line means y equal to mx plus c, or I would say, sir, ax plus by plus c equal to 0, sir. So linear means linear equation. Okay, but that's not the case. Okay, you're wrong. A linear function is defined as one whose coefficients are either constants or product of constants. Okay, that means the coefficient. So what we are having in an equation, we are having coefficient and we are having a variable. Okay, and this coefficient variable, these combination only will going to make an expression or equation. Okay, so the linearity assumption limits variables. Limits linearity assumptions will limit your variables, not the coefficients. Limit variables, not the coefficients, from having an exponent higher than 1. From having an exponent higher than 1. Because we assume that and it's been already notified for a linear, the degree of the variable should be 1. Okay, degree of the variable should be 1. But who is going to limit them? Who is responsible to limit that the degree of variable is going to be 1? Okay, we haven't studied, sir, this concept, sir. We haven't studied, sir, before, sir. So if I say f of x equal to a plus b plus c into 4, for example, this is your equation, a plus b plus c into 4. And if I say gx equal to beta into x1 plus alpha square into 2x. Now, a, b, c, beta, and alpha all are real numbers. Okay, are both linear functions. These both are linear functions, while f of x square is not a linear function. You know that the degree of variable x okay, here it's what? It's 1. Okay, it's 1. Also, one more thing, a plus b plus c into 4. See, this is also a linear function. It doesn't have any variable here. A, B, C are the some numbers. These are the real numbers. They are not some associated with some some variable here. Okay, so the point is, linear function is a function where linearity assumption limits variables, not the coefficients. We don't have any limitation for the coefficients. Only variable limitation is there, that it should have a power 1. That's it. Okay, so without any variable also this is a linear function, and with a variable this is also linear function, but there is one twist. If I'm having x square now, this is quadratic in nature. This is now not a linear function. Okay, but the point is we are studying about the linear algebra, so obviously we are expecting these kind of equations. Okay, not this kind of equations. Next, inner product. I hope you students definitely know about your linear the inner product. That means you might be knowing about the dot product. Okay, so the dot product, what does this dot product means? If you are obviously, if you have studied about the vectors, okay, a dot b, you know that, then the product of a and b is equal to magnitude of a into magnitude of b into cos theta. That is the dot product. Usually that means as per the formula, as per the notation. So in that is also called as inner product. Okay, so dot product or inner product is an operation associated with a pair of vectors. Okay, so I am available with a pair of vector na, a and b, vector a and vector b, and if I need to find the dot product between a and b, then I am writing magnitude of a, magnitude of b dot cos theta. Now what is this cos theta? What is this cos theta? Here it is. A dot b upon magnitude of a into magnitude of b. That's what the cos theta means. All right. And theta is the angle between vector a and the vector b. And I need to calculate the cos of that. That will be representing the cos theta thing. Okay, so for example, here it's been shown in the visualization that you are available with the vector 135, you are available with the vector 246, and I need to perform the multiplication of these two vectors, and certainly I got some result. Okay, so here if I need to perform this dot operation, my result is 1.2 plus 3.4 plus 5.6. Okay, so 1 into 2, 3 into 4, and 5 into 6, result is 44. So how I'm going to get this result? On what basis I'm going to get this results? Just using the same formula which I told about. Okay, that is a into b. This is a scalar quantity, scalar results if I'm going to perform a dot product. And how I got this thing? See, a is ai into ai. That means a into a, repeated multiplication of a. Mod of a is a square root of a into I. You know that it's a square. That means magnitude ka squares. Sum of the magnitude ka squares ka root. That is your magnitude of a. Similarly, I'm going to calculate the magnitude of b, and that's it. And I need to apply them into the formula. And theta is the angle between a and b, and I need to calculate the cos of them. So a vector dot b vector equal to magnitude of a into magnitude of b into cos theta, and theta is the angle between them. That's it. Okay, norms, normalization. See, norms are essential concept in linear algebra because they provide a way to measure the size or magnitude of the vector. I need to measure the size and magnitude. Remember, you should be alert. Okay, magnitude, and I need to measure the size and magnitude of a vector. So different, there are various normalization techniques which are available. And normalization is very very much important concept in machine learning because it helps in dimensionality reduction. For example, if I am available with the data of many number of features, that means it is having high dimension data, I will be using normalization technique to reduce the dimension of my data set. Very, very important concept. Okay, so how to perform the normalization? There are various kinds of normalization. Okay, so here I'm starting with LP normalization. LP norm. It's denoted by P norm. Okay, and its formula is summation of xi, that means x1, x2, x3, x4 to the power p. So xi to the power p. Okay, that means x1 to the power p plus x2 to the power p, because here is a summation sign. Okay, so I'm just going to add all these features to the by taking power p, and ultimately I need to calculate the root, that means root with respect to p for them. This is lp normalization. And the thing is, the most commonly used normalization are L1 and L2 normalizations. In case of L2 normalization, I am going to calculate the square. Okay, previously you have seen a p. So here if I replace p with the square, 2 thing. Okay, here the value of p is 2, then it is said to be L2 normalization, and it is having a very popular name, Euclidean distance. I hope you have heard this name somewhere. Euclidean distance. Okay, so how to calculate Euclidean distance between the data features, data thing. Okay, so here is what I need to perform the normalization. This is Euclidean distance, L2. Okay, so L2 is your square of the values. Xi square means x1 square plus x2 square plus x3 square plus x4 square. Just calculate the sum of all of them, and okay, done. And then calculate the root. Okay, that is your L2. And what is Manhattan distance? It is L1 normalization. In case of L1 normalization, I need not have to calculate any square thing. I just need to perform the summation. That's it. That means x1 plus x2 plus x3. Just take a summation of them. This is Manhattan. Okay. So if I'm available with a vector thing, for example, I'm available with your AI plus bj plus zk. So for L2 normalization, I will be performing a square plus b square plus c square ka root. And for L1 normalization, I will be doing a plus b plus c. That's it. That's Manhattan distance. Okay, remember. All right. And choice of normalization depends upon the problem. Okay, whether you are what kind of problem statement you are working. So according to we are going to choose your L1 and L2 normalization techniques. All right. Outer product. Outer product. So we have studied about the dot product. I hope you also know about the cross product. Okay, if I'm having a dot b now, I'm also having a cross b, cross product. Okay, so this is called as outer product. So inner product and the outer product. Okay, so the outer product is a cross product. So if I say a cross b, so it will be like a dot b sine theta. Okay, and here is your outer product results are. This is how you need to perform. For example, you are available with the two vectors. Your outer product, remember what happened with the dot product thing. When I'm going to perform dot product of the two vectors, I got the result as a scalar quantity. But if I'm going to perform outer product between two vectors, I'm going to get a matrix. I'm going to get a matrix. No, it's not a scalar. I'm going to get a matrix. Ultimately, there is a word used here, tensor. Tensor product. That means now when you are going to perform the outer product, the result which you got now, that is of higher dimension. Your vector was of 1D, and matrix is more than this 1D. Okay, so it's a tensor. All right. So here the result which you got, a1 b1, then a1 b2, then a1 b3, then and so on. This is n cross n matrix. So this is actually the multiplication of two vectors. Okay, and you know how to perform the multiplication. All right. So ultimately this is 1D. Vector is 1D, or I would say in a simple term, just with a silent word, it's a 1D matrix. Okay, this 1D matrix is being multiplied now. It is converted into n cross n matrix. So this is n cross 1, this is 1 cross n. After multiplication, it got into n cross n. This is cross product. Okay, and here that's what the visualization has been showing to us. All right. So now dimensions increased. In case of dot product, we are getting only scalar. Here we are getting the tensor. All right. So so the point is we have the vectors of size this, and this is what we got in the result format. All right. Now the next thing is matrices. So we know about the scalars, we know about the vectors. Now let us talk about the characteristics of the matrices. Okay, so the point is, matrix is a collection of numbers arranged in a row and column format. Okay, and obviously we need to organize data in case of machine learning and the data science. So either if I am available with a single term, so I say okay, you are scalar. If I am available with the data with some access, then I say you are a vector term. If I am available with the data in n cross n format, okay, then I'm saying yes, you are a matrix thing. Okay, so matrix, and that means I'm going to organize the data into row and column format. That means they are widely used in linear algebra to represent the coefficients of linear equations. So if you are available with the linear equations, I can organize them into matrix format. So they keeps very much importance. Okay, and you have done a lot of tasks using matrices. All right. So matrix can be of higher dimension beyond two. It's not mandatory. We are having 2 cross 2. You know that 3 cross 3, 4 cross 4, 5 cross 5. Okay, any kind of dimensions we can convert a matrix into, and they are usually called as a tensors. So I hope if you haven't heard this word tensors previously, so today I'm introducing to you. So higher dimensional matrices are referred to as tensor. A tensor with a rank 0 is a scalar quantity. A tensor with a rank 1 is a vector quantity. And a tensor with a rank n is actually a tensor. Now it will convert it into, with 2 dimension, it's a matrix, then 3, then 4, and it will now tensor thing. Okay, so here it is. Here is the representation, visualization. Scalar tensor of rank 1, and so on. Matrix tensor of rank 2, and a tensor of rank n greater. That means for any matrix greater than n 2, that's a tensor thing. Okay, fine. So this is the representation. This is what we called as a matrix row column arrangement. Now there is one term, linearly independent. So what does this mean, linearly independent? Okay, I hope you have heard about this, linearly independent. See, a linearly independent vector x is one that cannot be represented as a linear combination of another vector in a matrix. Okay, that means I can't use this vector in a combination with another vector in a matrix. Now what sir, what are you saying, sir? We didn't understand. Okay, let us take an example. Okay, for example, let us consider this matrix. Okay, this matrix is having 1 2 3 2 and 2 4 6 3. That's what this matrix is having. Now if I represent it, for example, this is one of the vector, this is one of the vector. Okay, if you can see, this is 1 2 2 4. So if I multiply this 1 2 with 2, obviously I'm able to get 2 4. Okay, that means I can get this 2 4 by multiplying 2 with this combination. So obviously these are dependent with each other. This is dependent. Okay, and in the next case, what I'm going to do, 3 6 also have the same concept. That means if I multiply 1 and 2, I'm going to get 3 and 6. Again, this is dependent. But there is a red mark over here, 2 and 3. There is a red mark. Why? Because if I multiply 2 with here, next I'm going to get 4, but here it is 3. Okay, so here the rank of the matrix is 2, obviously, because we are having 2 rows. The rank of a matrix is 2 because it is having two linearly independent vectors. Okay, it is having two linearly independent vectors. Okay, so this is linear independence. Okay, when we cannot form the matrix from another, we cannot form vector from another vector, then it's said to be linearly independent, and that's what here it's mentioned. A linearly independent vector is one which cannot be represented with the help of another vector. I can't do that. Okay, so it's linearly independent. That's why here the rank of the matrix is 2, because this is 2, this is 3. We got 2 rows, okay, which cannot be created with any of the combination. Any of the combination cannot be completed. That's it. So you need to understand what is linear dependency. Now, matrix transpose. I hope you know this thing also, transpose of a matrix. That means if I convert row to column and column to rows, that is called as a transpose thing. So the transpose of a matrix is also useful in machine learning, because in most of the cases we need to organize the data in such a manner that I need to convert row to column, column to rows. No, obviously transpose is required. All right, so here in this visualization, it shows the transpose. Here it is, transpose of a t to the power t. So transpose is represented by a to the power t. Okay, and here are some more representation. Diagonal matrix means that means, okay, let us first help in understand equivalent form of a matrix. Okay, equivalent form of a matrix. So for example, this is an original matrix. This is an original matrix, 3 7 4 2 8 9 6 5 8. This is your original matrix. Okay, And this is equivalent form of a matrix. Equivalent form of a matrix means I am going to reduce my matrix in such a way that I should be having number of zeros more. That means I'm going to apply some transformations over my matrix. Okay, and I'm looking forward to get I'm looking forward to get some. Am I audible?
Yes, sir.
Yes, sir.
Okay, so let me reshare the screen. So from where you missed the concept, that means what I was teaching, from where you missed it. Am I audible properly?
Yes, sir.
Okay, so from where you missed the concept, did you understood this thing, this rank of the matrix? Okay, you were listening at the time. Rank of a matrix, matrix transpose.
Yes, sir.
No, sir.
Okay, matrix transpose. Okay, let me re-explain the matrix transpose thing. Okay, let me re-explain. See, the point is matrix transpose. You know that converting rows into columns and columns to rows is called as a matrix transpose. Okay, and it's been a more requirement in case of your data science and the machine learning. There are many other things also in case of this your matrix operations. One is the reducing a matrix to echelon form. So how to reduce a matrix into echelon form? The point is, if you are available with the original matrix, for example here it's given 374 289 657. Okay, so what is the echelon matrix? See, echelon matrix is something I'm going to consider the last row, and most probably I need to perform some kind of operations in the rows. Okay, so that it should be converted into your most of the zeros. So here you are seeing that 0 0 1, and then in the second row you are seeing 0 2 5. Okay, so I'm trying to convert whatever the operations possible over the rows or the columns to make or to simplify my matrix, my original matrix. Okay, and then I am further reducing this echelon matrix so that my all the terms is going to be like 1 and 0 only. In diagonal, I am getting the ones. Okay, so it everything depends upon the kind of the operation which you are going to perform over the rows and the columns. This will make your echelon matrix. Okay, so this is your further reduced echelon matrix. All right. Now we will consider these things ahead. Okay, so the transpose is clear that we need to switch the rows into columns, column things. Okay, and and it is been denoted by a to the power t transpose. Okay, now transposing a matrix can also help in simplifying certain computations such as finding eigenvalues, because these are very much important. Eigenvalue, eigenvector, because there is one of the steps required prior to get the eigenvalues and the eigenvector. These are your transpose, and also to find the trace of the matrix and the derivatives of the determinant. For that purpose your transpose is required. So the trace actually is defined as the sum of the elements on the main diagonal. Okay, so whatever be the elements which are present in the diagonal now, if I am going to add it now, so that is called as a trace. Okay, that's the trace thing. Fine. And related to the derivative of the determinant, that is useful for proving the statements about the matrix algebra. Okay, so if I need to relate or some statements, some prove some statements in the matrix algebra, so need to perform derivations of the determinant. What are the values which are present in determinant, I need to perform the derivatives of it. So for that purpose it's also required. Determinant. So these are some terms related to the matrices. We'll further explore it more ahead. Determinant. So you might be knowing all the determinant now. That means various values which are written under two big bars, two bars. That is a determinant. Okay, so it's a crucial mathematical tool in matrix algebra, which is having multiple applications. It is a scalar value. Okay, that can be calculated for square matrix. Scalar value that can be calculated for square matrix. And square matrix means a matrix which is having same number of rows and the columns. That is called as a square matrix. So determinant has a number of interesting properties. It has been very much important. Determinants. Okay, and the most of the important application for the determinant in ML is the calculation of a covariance matrix. Again, very much important. Very much important. Covariance matrix. So because why? Because a covariance matrix is very much crucial component in an algorithm which is named as principal component analysis, PCA, and linear discriminant analysis, that is LDA. So PCA and LDA, these are the algorithms, okay, which are usually used in your unsupervised machine learning. Okay, so here there are steps for the calculation of a covariance of a matrix. So determinant keeps importance in the calculation of covariance matrix. So as I already told you previously also, that these all algorithms are prepared over mathematics only, over maths only. So if you need to derive these algorithms now, you require these matrices, operations over the matrices, determinants, covariance matrix, eigenvalue, eigenvector. So if you know all these terms now, then only you can understand these algorithms. All right. So, principal component analysis and LDA that I'm going to discuss later ahead. But you should be knowing, okay, these two algorithms, unsupervised algorithms, they require covariance matrix, and determinant is being helpful for calculating that. Okay, so here is the concept for the determinant, and we can organize the values in the determinant. In determinant, that means the scalar values. We can organize the scalar values in the determinant. Okay, so the point is, for example, if I am available with a matrix that is a 2 0 -1 -1 1. So the calculating how to calculate the determinant of this particular matrix. How to calculate the determinant of this? Again, let me show you. Here is your matrix 2 0 -1 1. So you know that I need to multiply 2 with 1 and minus 1 with 0. Okay, 2 with 1 and minus 1 with the 0 thing. Okay, so what will be result? 2 ones are 2, minus of 0 into minus 1, that will be 0. Result should have been 2 here. It's been mistakenly written as 3. Okay, so please ignore the mistake. Kindly ignore the mistake. All right, here the result should have to be 2. So, it's a cross multiplying the things. Determinant solving. You might be knowing about the determinant solving things. I'm just following the same approach for the determinant here. All right, now eigenvalues and the eigenvector stuff. Very much important. So, eigenvectors and eigenvalues are incredibly important concepts in a linear algebra, and they are used for extensively in many of the cases of maths and the science, and these are the basic foundation for machine learning. Okay, so if I do talk about eigenvectors, they are used to represent the direction along with the linear transformation. Okay, vectors which represent the directions with a linear transformation, they are called as eigenvectors. While eigenvalues just gives us the information about how much linear transformation has been performed. So just remember the definition. Eigenvectors represents the direction, and eigenvalue are only the values. See, we already know that scalars means values, vector means value with the direction. So here also the same concept. Eigenvalues means the values, and eigenvectors are the values with the direction. And here we are relating the terms related to the transformations. Okay, linear transformation. Okay, so something related to the linear transformation with the scalar quantities, then it's eigenvalues, and something related to the transformation with the vector quantities, then it's said to be eigenvectors. That's what the thing is. All right. So what is this eigenvalue? Let us give an example. So eigenvalue is a scalar value. It is denoted by lambda. I hope you have already done in mathematics. Okay, it's represented by the lambda. Okay, so what are the steps to find the eigenvectors of a matrix? There are three steps. Find first the eigenvalue, put back into the equation, and solve the equation. This is how you are going to find the eigenvectors. Okay, so it's usually represented by a lambda eigenvalue. Okay, so the thing is, if I am having this equation, a dot v equal to lambda dot v, a dot v equal to lambda dot v, that means v is a eigenvector and we are trying to find its value. All right, so for example, here I am available with a matrix 1 2 3 minus 4. A is a matrix 1 2 3 minus 4. Lambda is a value. What value? Eigenvalue. And what is I is an identity matrix which is having 1 0 0 1. All right, now if I'm going to multiply this lambda inside, so it will be lambda 0 0 lambda. If I'm going to subtract these two matrices, I'm going to get the result as 1 minus lambda, 2 3, and minus 4 minus lambda. This is my characteristic matrix. Okay, so if you have been given a problem statement to find the characteristics equation and to solve it for the your eigenvalue and the eigenvector, this is the approach you need to follow. So first solve for the characteristic matrix. Okay, so here is my characteristic matrix. Then I need to apply the determinant over it. I need to apply the determinant of a minus lambda I. So multiplication of this with this minus multiplication of this with this is going to find me the value for your eigenvalues. Okay, so after performing this 1 minus lambda into minus 4 minus lambda minus of 3 into 2, this will going to give me the result. Okay, and I'm going to equate it with the 0. So first thing is you need to find the characteristics equation. Okay, and characteristics equation is simply a minus lambda I. I is your identity matrix, a is your matrix. Okay, given matrix. I need to find the eigenvalues and eigenvector for it. So this is how you are going to solve. So lambda 1 and lambda 2 are the eigenvalues. Okay, these are the eigenvalues. All right, and this is how your vectors are represented. Okay, with this visualization, it's showing the visualization for your eigen values and the eigenvectors representation in a plane. All right, now here the yellow and the green vectors can only change the size when they are going to perform some transformations. Okay, so the quantity by which the yellow and green vectors stretches or compress, They're determined by eigenvalue, and the direction is given by the eigenvector. Okay, eigenvector. So first find the eigenvalues, and then what next you need to do? You need to plug in back the eigenvalues and solve the system of equation. Okay, so I need to again plug in the values in this equation. I need to again plug in the value into this equation. This is your characteristic matrix, and there will be an equation formed with respect to, yeah, here it is. A dot v equal to lambda v. This will be your equation, and again going to put the value of lambda. So first I'm going to put the value of lambda as minus 5, then I'm going to put the lambda for 2 in this equation, and obviously this will be system of linear equation. And then I can just prepare a vectors, two vector I'm going to prepare, and these two vector will be my eigenvector. So first convert it into, first find the characteristic equation, solve the characteristic equation, get the eigenvalues, resubstitute the eigenvalues here, and find the vectors. Create two more vectors on the basis of value, because 2y, because lambda 1 and the lambda 2. If I do put them here again, I'm going to find the two more equations. Okay, so that will be the vector thing. Okay, so very much important, eigenvalues and the eigenvectors, remember. And as I already told, that eigenvectors and eigenvalues are very much useful, and one of the algorithm I did talk to you about, principal component analysis. So this PCA stuff, principal component analysis, this it requires a step of eigenvalue and the eigenvectors along with the covariance matrix. So definitely I'm going to use it. Okay, now the next thing is, let us have again some further discussion. Okay, over the vector and matrices, I need to explore these concepts again ahead. Okay, because these are the only things which are used in the linear algebra. Okay, so vector vector is defined as an element in n-dimensional coordinate system. Okay, you are having n dimensions, and I need to represent it in those dimensions. Okay, so that will be a vector thing. For example, if I do consider a 2D plane, and I need to represent a point xy in that 2D plane, so wherever that point is located now, I need to calculate from the origin and make a vector, or make a line pointing to that particular point from the origin. That will be a vector. So it can be 2D, it can be 3D, if I'm having a coordinate xyz. Okay, so for example, x1, x2, x3, xn, this is a vector. And if I take a t now, that will be the transpose of the vector. You very well know about that. And this is the result which I'm going to get, converting columns to rows. Okay, so this is a vector transpose. All right, and here is your matrix of m cross n. Okay, that means m rows and the n columns. Okay, this is m cross n matrix, m rows and n columns. Okay, and here is your transpose of a matrix. So I can calculate the transpose of a vector, I can calculate the transpose of a matrix, it's up to me. Okay, here is the transpose of this matrix. All right, rows converted to columns. All right, now the thing is, as I already told you previously, tensor, I took a name, I took a word, tensor. So high dimensional matrix is called as a tensor. As per our discussion, what it said, high dimensional value is a tensor thing. All right, so the point is, this is a tensor, this is a matrix. If I'm going to represent this 1 2 3 2 1 7 and 5 4, this is a tensor thing. All right, representing matrix inside a matrix is called as a tensor. All right, so this is 1D tensor, this is 2D tensor. That 1D means one dimension, 2D 2 cross 2, 3D 3 cross 3, 4 cross 4, and 5D, and so on. All right, in case if I get disconnected via line, okay, so here there's a power issue. So remaining stuff I will again teach you in the next class, in case if I'm going to disconnect any time I can. Okay, so remaining stuff I will teach you in the next class. Just hold on. All right, so this is your tensor representations. Fine. Now, operations on the vectors and the scalars, we have seen some of the properties of the vectors and scalars both. Okay, that is your commutative, associative, identity, inverse, all we have seen. Okay, so for example, if I need to perform the operations over the scalar stuff, okay, so cd a equal to cda. See, this is how we are going to perform. Okay, that means any operation with the scalar is performed with every element of a vector, every scalar, every vector. Okay, so if C and D, these are the scalars, capital A is a vector. So, I can, if I'm going to multiply CD first and then I need to apply over A, that will be similar to